In this recording, we're going to introduce rational functions. First off, what does it mean for a function to be rational? Well, let's define it. So we're going to define a rational function as a quotient of two polynomials. Okay, so of course, the denominator of any fraction can't equal 0. All right, so how do we show that a function is, in fact, rational? We have here a complicated looking function here, and we want to show that it is, in fact, the quotient of two polynomials. So we want to get it into a form where we could identify the f and the g. So after we do that, we're going to find its domain. So what we want to do is get this out of its complex fraction form. So I'll give you a second to jot this one down. All right, and I've shown you a couple different ways to simplify complex fractions. One way we've shown is to turn it into a division question. You can do that, but you have to first combine the denominator into a single fraction, and then turn it into division. That way still works if you like it. If you'd like to try a new way, I think this way is slightly easier. Okay? What we're going to do is look at the denominator here of the little fraction that we're going to try to get rid of. And if we multiply all terms by that denominator, all terms in this fraction, we're going to eliminate this little denominator. So we're going to come over here and multiply by x. We're going to multiply by this one by x, except I'm going to write it as x over 1 to show that it's really the numerator that I'm dividing, that I'm multiplying by x. Those are going to divide out. And then I'm going to multiply the numerator by x. Okay? So multiply all terms by x, because essentially what I'm doing is multiplying by x over x, which we understand to be a 1. So I'm not changing its value. So what does this thing look like? We still have a 1 over to the left side, but now your numerator is an x, and your denominator is an x squared. Well, those divided to 1, so it's just x squared minus 1, right? Okay, so then we want to combine these because we still don't have f of x over g of x like we wanted. We wanted to get it into this form where we have a polynomial over a polynomial. So we're going to combine these fractions. Hopefully you remember how to do that. We're going to turn this to a fraction over 1 and then multiply by something, some form of 1, to get a common denominator. And from there it's going to be pretty easy for us. Why don't you finish it out? Play the recording when you're ready. Okay, so we've done it. We've shown that, in fact, f of x is the quotient of two polynomials. And now we just need to find the function's domain. So the domain of the function is all values that don't make this undefined. So we can figure that out a couple ways. First off, we can look at the table and see if we see any values that produce an error. Okay, that's a nice little check. But sometimes they might be values that are fractions. So it's not a totally reliable way. It's better off used as a check. Okay, so to find the domain, okay, first in the new equation, where the denominator is going to be equal to 0. So go ahead and solve this out. Difference of two squares, x minus 1, x plus 1. Okay, there's another consideration though. All right, so let's just label this up a little bit. In the new equation, we considered that. And then in the original equation, we had to consider that little fraction there. So 1 over x. When does x equals 0, where x equals 0 and x equals 0, right? So we have these three places at 0 and -1 and 1 that are problematic, okay? And so that, again, came from that little place in that original fraction. So the domain is all real numbers such that they are not equal to -1, 0, or 1. So you can say it like that. If you were to write this in interval notation, we talk about that. Okay, basically, I'll just kind of make a graph up here. We're speaking about a number line that excludes 1, 0, and -1, right? So those are the open places on the number line, and everywhere else it can exist. Just can't be those places because they would make a denominator that's equal to 0. So basically you have 1, 2, 3, 4 separate intervals that you're going to need to state here. But interval notation is pretty easy once you understand it, because you just say the starting point, which on this arrowhead is a -infinity, and then the ending point, which is -1. Round parenthesis because we're dealing with an open circle here. And then you put a union in between to mean or. So just continue to state all the intervals. Okay, so there's our interval notation for that same domain. Thanks for watching.